Hello everyone and welcome. Today, we're exploring a core concept in computational chemistry and biology, the force field. It might sound like something from a science fiction movie, but it's a real and powerful tool that scientists use to understand the molecular world. So, what is it? Imagine you want to study a protein, which has thousands of atoms. Calculating the behavior of every single electron with quantum mechanics would be incredibly accurate, but it would take a supercomputer years to simulate just a tiny fraction of a second. It's just too slow. This is where force fields come in. A force field is a simplified model. It's a set of rules and equations that lets us predict the energy and behavior of molecules much, much faster. The most popular analogy is to think of molecules as being made of balls and springs. Each atom is a ball with a certain size and charge. The chemical bonds connecting them are like springs. This ball and spring model allows us to use classical physics, like Newton's laws, instead of complex quantum mechanics. A force field is essentially the instruction manual for this model. It has two main parts. First are the bonded terms. These describe the energy it takes to stretch or compress the bond springs, the energy it takes to bend the angle between three connected atoms, and the energy associated with twisting or rotating around a bond. The second part covers the non-bonded terms. These describe interactions between atoms that are not directly connected. This includes the van der Waals forces, which you can think of as the personal space of atoms. They attract each other from a distance but repel if they get too close. It also includes electrostatic interactions, which is the classic rule of opposites attract for atoms with positive and negative partial charges. So, a complete force field is a collection of equations for these interactions, plus a huge list of parameters, like the ideal length of each bond, the stiffness of each spring, and the charge on each type of atom. Scientists develop these parameters by carefully comparing them to experimental data or more accurate quantum calculations. By adding up all these individual energy contributions, the computer can calculate the total energy of the entire molecule for any given arrangement of its atoms. From that energy, it can determine the forces on each atom and predict how the molecule will move, vibrate, and change its shape over time. This is the engine that powers molecular dynamics simulations, allowing us to watch proteins fold, drugs bind to their targets, and materials assemble themselves, all inside a computer. So, in a nutshell, a force field is a clever, fast approximation that makes it possible to simulate large molecular systems. It's the essential tool that bridges the gap between the atomic scale and the complex biological processes we want to understand. Thank you so much for watching. If you found this explanation helpful and want to learn more, please consider liking this video and subscribing to support the channel. It really helps us create more content like this.